Hello everyone. In this video, we're going to be solving a radical exponential equation. So we have the square root of 77 to the power x minus 121 to the power x, and that is equal to 7 to the power x minus 11 to the power x. Notice that 77 is 7 times 11, and 121 is 11 times 11, or 11 squared. So let's go ahead and use those facts to our advantage, and I'd like to use substitution. You could also just square both sides and kind of try to factor this expression, which is factorable by the way, but I like to use substitution. It's going to simplify things a great deal. We're going to be looking at real solutions as well as complex solutions. Okay? All right, let's get started. So I'm going to call this 7 to the power x. I want to call that a, and I want to call this b. So 7 to the power x equals a, and 11 to the power x equals b. And now we're going to be able to write everything in terms of a and b, and then we're going to simplify that expression, okay? 77 is 7 times x. So 77 to the power x is 7 to the x times 11 to the x by using properties of powers or exponents. So this means it's going to be ab. And 121 to the x is basically 11 to the x squared, and that will be b squared. Let's go and make the replacements, and then we'll simplify our expression. So square root of ab minus b squared is equal to a minus b. Awesome. At this point, it makes sense to factor this expression or square both sides. Let's get rid of the radical. That's better. So I'll square both sides, and then this removes the radical. And now on the right hand side, I kind of come up with something a squared minus 2ab plus b squared. Let's not expand it though, because like I said earlier, this is factorable. How? If you factor out a b is a common factor by the way, you get a minus b, and you have a minus b squared here. Let's go ahead and put everything on the right hand side. So let's move this stuff, and that's going to give us a minus b squared minus b times a minus b equals 0. All right, now what do we do with this? We were trying to factor, remember? So a minus b is a common factor. So we're going to take that out. And then from here we get, to get a minus b squared, we do need another a minus b minus b, right? And that would be 2b. Yay! 2b or not 2b. So we get a minus b and a minus 2b as our factors, and since the product is equal to 0, which is nice by the way, we can safely say that a minus b is equal to 0, or a equals b, and from here we can say that a is equal to 2b. Okay, let's go ahead and take a look at each of these equations in terms of x, because obviously we use substitution, so now we have to back substitute. So what is a and what is b? Remember, a is 7 to the power x, and b is 11 to the power x. And as soon as you solve this problem, how is that possible? Two different bases, same exponent, and they give you the same result. It's only possible if x is equal to 0, right? In the real world, of course. So from here, you can safely say that, hey, because 7 to the 0 and 11 to the 0 are both equal to 1, this means x equals 0 is a valid solution. Okay, it's real. Now, let's go ahead and take it to the complex world. So we want to complexify things a little bit. So here's what we're going to do. Obviously, nothing complex is going to come up from here. So we're going to do the following. Since 11 to the x can never ever be 0, we're going to divide both sides by that. Let's go ahead and do it. And when we do, we get 7 over 11 to the power x. So I kind of use a common exponent equals 1. Awesome. Again, you might say, hey, what is the big deal, right? X is going to be 0 and we get the same answer. Yes, in the real world, but in the complex world, 1 can be written, and be very careful about this, 1 can be written in infinitely many ways, right? And those values are basically going to be like separated by some argument, right? So let's see how that works. So in the complex world, 1 is basically 1 plus 0i, in other words, 1 comma 0. So it's like a point on the real axis, 1 unit away from 0. So that means it makes a 0 radian angle, but you could also interpret it as 2 pi, because 2 pi would be equivalent to 0, or 4 pi, or just multiple of any integer multiple of 2 pi. In other words, we can use Euler's formula and write this as e to the power 2 pi ni. Remember, e to the I theta gives you the polar form of a complex number using Euler's formula. Theta represents the angle, and I is just the imaginary unit. And that's what we did. So here, the angle we're talking about is integer multiples of 2 pi. All right? And this is really cool because now let's rewrite it. 7 over 11 to the power x equals e to the power 2 pi ni. All right? Some people write it as 2 and pi I, same thing. Now we're going to go ahead and natural log both sides. When we log both sides, though, we have to be careful because there's going to be, and by the way, the modulus for this number is 1, so it's going to be like 1 times this. Normally, you're supposed to write it like r e to the theta. And when you ln something like this, you're going to get a real ln and a complex ln, which is going to be the I theta, because you're logging a complex number. So that's a little different. But same rules pretty much work. And here, when we ln both sides, we should be getting ln 1 is going to be 0 because that's the real ln. And when you ln this expression, it's just going to be the exponent, which is 2 pi n I. And at this point, you are able to get the x value because you can go ahead and move this x to the front, multiply by ln something. This is a real value. And then, of course, you want to get the x by itself. So let's go ahead and divide both sides by ln 7 over 11. But since we want to kind of separate the real and imaginary part, we want to write it like this. And just kind of separate the I. So that's going to be the imaginary part. But this number has no real part because its real part is 0. What is that supposed to mean? It just means that if n is equal to 0, x becomes 0, which is the real solution. We already found it. If n is equal to 1, for example, then x is going to be 2 pi over ln 7 over 11 multiplied by I. And that's going to be an imaginary solution. And of course, there are infinitely many solutions because there are infinitely many integers which you can replace n with. Make sense? All right, great. So let's go ahead and take a look at the second branch, not the second method, because we only solved this one, which is a equals b. Now let's go ahead and take a look at a equals 2b, or not 2b, a equals 2b. And remember, a is equal to 7 to the power x, and b is equal to 11 to the power x. If you plug it in, 7 to the x equals 2 times 11 to the x. And again, we're going to isolate both sides, but this time let's just go for the complex because the complex solution is going to give us the real one as a specific case. And I can just go ahead and write this as 7 over 11 to the x equals 2. And how do you complexify 2? Similarly, you can just multiply this by e to the power 2 pi ki. Remember, e to the power 2 pi ni or 2 pi ki always represents 1. And there are infinitely many ways you can represent it. And now let's go ahead and natural log both sides. And then we're going to get the x value. And this is going to be ln 2 plus 2 pi ki. Remember, if you natural log this, you're going to get 2 pi ki. And then we're going to get x ln 7 over 11 equals ln 2 plus 2 pi ki. And then by division, you can get x equals ln 2 over ln 7 over 11 plus 2 pi k over ln 7/11 times I. And as before, if n is equal to, or k, I should say in this case, if k is equal to 0, x becomes ln 2 over ln 7 over 11, which is a real solution. Okay? And of course, for any k value besides 1, you're going to get infinitely many complex or imaginary solutions. 2 real, infinitely many complex solutions to this equation. And this brings us to the end of this video. Thank you for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.